Hello, this is our second lecture on deadlock. The first lecture talks about deadlock prevention. The key idea in deadlock prevention is we make sure one of the four conditions will be violated. These conditions are mutual exclusion, no preemption, hold and wait, and circular waiting. Because if a deadlock happens, then all four conditions would hold. Now, if one of them fails, deadlock will never happen. As a result, when we design our program, we make sure resource or process will not be holding something and at the same time requesting something. Or if we are able to make sure no circular waiting, then there will be no deadlock. So in this second lecture, we talk about deadlock avoidance. What does that mean by deadlock avoidance? It means we do not deal with hold and waiting and the circular waiting directly. Instead, we design a central algorithm. Every process when it's going to make request to use resource must go through the central system. Therefore, the central system knows which process has something and needs something else and how many. This algorithm will be discussed in this lecture. This algorithm will guarantee deadlock will never happen. So deadlock avoidance means we do not explicitly prevent it from happening. Instead, we design an algorithm. A process must go through it before it can get the resource. The key concept in the design of deadlock avoidance algorithm are safe sequences and a safe state. What is a safe sequence? Let's assume that each process provides the maximum number of resources of each type it needs. For an example, when you design a process, you probably know what kind of resource you will be using. For an example, you will need maximum space of say 2 GB, and you need 10 tape drivers, 2 disk driver, and so on. So before your process runs, it must provide this maximum number of resources of each type it needs, even though you don't use all of them at the same time. Now, there are algorithms that can make sure the system will never enter deadlock state. This is deadlock avoidance. So let's define the concept of a safe sequence. A sequence of processes, P1, P2 to Pn, is a safe sequence in this order. Formally, it means for each process I in the sequence, its resource requests can be satisfied by the remaining resource currently available and the sum of all resources that are being held by P1, P2, and to Pi-1. In other words, for every process in the sequence, say, let's say Pi, the system will still have some resource in hand. So Pi is there if and only if all of the processes have already owned something. If all of the resource being held by process prior to Pi plus the remaining available resource in the system is good enough for Pi. For an example, P1, no problem. P1 does not have any processes before it. So if P2 is here, it means the currently available resource plus the resource being held by P1 is good enough for P2. The next process, P3, after P2 means the current available resource plus the resource being held by P1 and P2, the sum of these two owned by P1 and P2 and the currently available resource are good enough to run or to satisfy P3's request. So if we could arrange the processes in the system in this order, then we have a safe sequence. Then we talk about safe state. A state is safe if the system can allocate resources to each process in some order and still avoid a deadlock. Therefore, according to safe sequence, we could allocate resources based on the order given in a safe sequence. Then every process would run and release its resource, allowing the next process to run. Therefore, a safe sequence guarantees that the resource allocation is safe. That is no deadlock. So if the system can find a safe sequence, the system is in a safe state. Otherwise, if no safe sequence exists, the system state is unsafe. Now look at this diagram. The system has two states, safe and unsafe. If we don't do anything and allocate resource in some arbitrary way, the system could be safe and sometime veering into unsafe and then going back to safe and unsafe and so on. If for some reason we have a deadlock, of course, a deadlock occurs because it is unsafe. We have no way to allocate resource to rescue the system from an unsafe back to safe state. So an unsafe state may not be a deadlock state, but a deadlock state is an unsafe state. So deadlock avoidance algorithm simply run the system and make sure that the system is always in the safe state and never enter the unsafe state, let alone the deadlock state. So this is the meaning of safe state. Therefore, to avoid deadlock, one way to do that is we always make sure a safe sequence can be found. Now let's take a look at an example. We have a system. This system has 12 tapes and 3 processes, A, B, and C. At time t0, we have the following allocation. A, B, C needs maximum number of tapes 10, 4, and 9, respectively. And now the system currently allocates 5 to A, 2 to B, 2 to C. So A would need 5 more, B would need 2 more, and C would need 7 more, because currently holding plus what we need is exactly the maximum. So is this system state a safe state? Well, the answer is yes, because we should be able to find easily a safe sequence here. The answer is at least BAC. Why? The system has already allocated 5 plus 2 plus 2 tapes. That is 9. Therefore, the system has 3 free tapes available. 12 is the system's available resource initially. So currently, the system has 3 free tapes available. So let's scan the need array. A needs 5, but currently the system has only 3, A cannot run. But system can run B because B only needs 2. So when B needs 2, the system allocated 2 to the current holding, making B to have 4. After B is done, B would return 4 tapes. So when B returns 4 tapes, so how many available there? Now look at here. B has already have 2. Now 3 free tape given to 2 to allocate it 1. So 3 minus 2 is the situation where B, after B receive the 4, then B would return 4. Therefore, the system would have 5 free tapes. So B is done. Now let's scan the list again. A needs 5, so we could run A. After A is done, A would return 10. Then 10 is good enough to run C, because C only needs 7. Therefore, we have constructed a safe sequence B, followed by A, followed by C. Now, suppose the system still has 12 tapes and still 3 processes. At some other time, say T1, C for some reason received 1 more tape. So originally C has only 2, but now C has 3. Then what C would need would be 6. So the total number of tape allocated would be 5 plus 2 plus 3. And we have only 2 free tapes. Now in this state, is the system safe? Well, let's try. We have 2 free tapes. We scan the list. We cannot run 5. 5 is larger than 2, but we still can run B, right? So after giving B the 2 tapes, and then B runs, and finally B would return 4. So now the system has 4 free tapes. But the system for A, it needs 5. For C, it needs 6. So A cannot run because its request or need is larger than the system available. We cannot run C either because C would be 6, and then we only have 4. So in this system, we don't have a safe sequence. And actually, it is a deadlock. Process A and the process C cannot run. So why we get this? It is because for some reason, the system assigned or allocated 1 more tape to C, causing the system going from the previous safe state into an unsafe state, but actually it's a deadlock state. So a deadlock avoidance algorithm tries to eliminate this incorrect allocation. So hopefully before we go on, you will review these 2 examples. So what the algorithm we're going to talk about for deadlock avoidance, this is the so-called Bankruptcy algorithm. This algorithm, well, proposed by Dijkstra again. Dijkstra is a very commonly seen name in operating system design and concurrency. The Bankruptcy algorithm was used in Dijkstra's THE operating system. When we talk about semaphore and the monitor, we learn Dijkstra's THE system. So Dijkstra's algorithm was probably the earliest operating system that can have a provably true deadlock-free situation. The deadlock avoidance algorithm makes sure that the system is always in a safe state. Therefore, no deadlock can occur. Because a system is in safe state, it has a safe sequence. The resource allocation, we just run P1, and when P1 is done, we run P2. When P1 and P2 is done, then we simply run this process in a sequence. Then we don't have deadlock. So resource requests are granted only if in doing so, the system is still in a safe state. As a result, resource utilization may be lower than those systems without using a deadlock avoidance algorithm. As we mentioned, if we have a safe sequence, P1, P2, P3, then we run P1, followed by P2, followed by P3 in a sequential way. Of course, it does not have to be that case. This is a worst case. We run P1, followed by P2, followed by P3, then no deadlock will occur. So here, you know, the most important thing is we need to decide in the algorithm to find a safe sequence. Surprisingly enough, the algorithm is very simple. Before we can go for the algorithm, let's take a look at the idea of banker's algorithm. Suppose you are a banker with a limited amount of money currently in your hand. If customer A wishes to borrow X amount, and if you have no less than X, A, of course, if you have no less than X, A can have it, of course. So in your hand, you have your current amount minus what A is. That's your current minus X. If you have less than X, we have a problem. For an example, if X, that A's request is $500, but you have only $450. In that case, of course, A's request cannot be satisfied. It must wait until other customers pay their loans off so that you get more money in your hand until you have sufficiently large amount to satisfy A's request. Here, assuming that A does not need this money in an urgent way. Now, a real example. Suppose you have $1,000 in hand. Your three brothers, Adam, Bill, and Chuck, borrowed $400, $300, and $100 from you respectively. So you have only $200 in hand. Now, what if Adam asked for $600 more? Of course, you cannot satisfy Adam's request because you only have 200. But you think if Bill and Chuck will return their $400 and the $300 respectively, assuming everyone is honest, you will have enough money for Adam. In this way, you just ask Adam to wait until Bill and Chuck return the money. So this is the basic idea. To implement this safety algorithm, we need some notation. First of all, the system has M resource types. The value M is, of course, fixed because your hardware is always fixed. And each resource type has several units. This is also a fixed value. For example, the system has 10 tape drivers and a 5 disk driver. So these values are always fixed. However, the system has N processes. The number N could change from time to time. Each of these processes declares, before they run, each of these processes declares its maximum needs. Although these resources may not all be used at the same time. Then the deadlock avoidance system requires several matrices to keep track the state of resource allocation. These matrices are the following. The first one is available, one dimension, max allocation need are two dimensional. The available array has m entries, 1 to m. One entry for each resource. Here, available I equals k means the system has k units of resource type I available. So if available 3 equals 10, it means the system has 10 units of resource type 3 available. Now, maximum has n rows, 1 row per each process, m columns, 1 column for each resource type. So this matrix is referred to as the maximum demand of each process. So max I comma j equals k means process I needs maximum k units of resource j. Now let me repeat. Max I comma j equals k means process needs maximum k units of resource I. If you are used to this type of interpretation, the remainders all the same. So the array allocation indicates which process has how many units of which types. So this is refers resources allocated to each process. So allocation I comma j equals k means process I is currently allocated k units of resource j. And finally, this is the need array, the remaining resource need of each process. Here, need I comma j equals k means process I still need k more units of resource type j. So it's obvious for each process, this is the allocated one, this is the future need. And because each process has its maximum need, therefore maximum is equal to the currently allocated plus the future need. So if you know max and either one of them, you can compute the other. Of course, in implementation, the max array is user input. And allocation is the system allocation record, filled by the system. And this is the computed array from max minus allocation. Now, we have a notation. We usually use a, I comma star to indicate the ith row of matrix A. Given two one-dimensional array, 1, A and B of the same size, we write A less than or equal to B if and only if for all I, AI is less than or equal to the corresponding elements in B. Now, if the two arrays are two-dimensional of the same size and same shape, then we write row I of A is less than or equal to row I of B if and only if for every element on row I, Aij is less than or equal to Bij. So we'll use this notation to present you an algorithm for finding safety sequence. Here it is. Look at it, this is very, very simple. For convenience, I use words rather than algorithms because this is easier to explain. You can easily convert to any language. We need two working array, one work. It has m entries, one for each resource type. So work I equals K means the system has K units available for resource type I. Finish has n entries, one for each array. So work, the array work is actually a working array available, so that we do not have to ruin the system array available. So work is local to the safety algorithm. So initially, we copy the system available to work and set every entry of the finish array to false. This means none of the process has done. They are still working, waiting for getting the resource. So now, step 3, for an I, that is, you find a value I, a process, find a process I such that its finish element is false, meaning it's not yet done, and its need is less than or equal to work. That is, whatever process I would need in the future is less than or equal to the current available resources. If you can find such an I, we go to step 4. If you couldn't find such I, either several of them would have finished to be not false, and or the need is greater than work. So keep this in mind. These two conditions are connected by an N. That is, you're going to find an I such that finish I is false, and a process I's need is less than or equal to work. If no such I can be found, go to this step. If you can find such I, then we pretend we could run it. So after running this process would return whatever currently allocated to it. In other words, process I would run and the finish. So process I allocated stuff would be returned to the system available. So update the system available. Because of this, process I is done. We set its finish I to true and go back to find next I. So basically, we simply search the array, process array, to find a process whose finish is false. Thus, it's not yet done. And at the same time, its needs is less than or equal to work. So this process can run. After running it, it will return its allocated resource so that the current working array for the system available resource could be updated and it's done. Then we find next one. Sooner or later, you won't be able to find such an I. So we go to step 5. If finish I is true for all I, the system is in a safe state. Why? Let's take a look. Again, remember the safe sequence is the first one runs, the next one wait until the system available here plus all processes before it would return their resources. So if I find one and the current system resources available, then I could run it and then return my resource and I'm done. And next one, so the one we find it here, I here is one more process in the safe sequence. Now, please do not advance to the next one. Hopefully, you will study this algorithm carefully before move on to the examples. If it's needed, please pause. So now you know the safety algorithm. Now, the banker's algorithm simply calls a safety algorithm. Hopefully, the safety algorithm would return the system is safe. Then the request can be allocated. The banker's algorithm will use the 4 arrays we mentioned earlier: available, max allocation, and a need. But we need one more array, request, whose dimension is the same as max allocation and the need. Its purpose is to record the resource request by each process. Here, request I, j equals k. It means process I requests to use k units of resource type j. So these are data structures to be used by the banker's algorithm. Now, if a process requests to use some resources, the process builds an array of m elements, where xj equals k means process I would need k units of resource type j, and array x would be used as the only argument when we call request. Remember, the system model would be request and use and then release. So if process I gets a resource and then uses it, finally, when process want to release the resource, process ji calls procedure release with a single argument x, where xj equals k means process I releases k units of resource type j. So that is easy. So the banker's algorithm goes as follows. Process I calls process request x with its resource needs. The resource request algorithm uses x to update the request matrix. And then the resource request algorithm runs the checking procedure by calling the safety algorithm to determine whether this request can be allocated and system still safe. If the safety algorithm says it is safe, the process get the resource. Otherwise, the requesting process here, process I, will be blocked until the process can get the needed resources later, after some processes releases their allocated resources. So the algorithm itself is simple. As we mentioned, request is the 2-dimensional matrix is a request matrix. When process I calls request procedure, it provides what kind of resource it needs. So resource request uses that argument to update the request matrix. Now we make some error checking. If the new request is less than or equal to the need array, that is, the need array indicates the future needs of process I. So the request by I must be less than or equal to its future need, of course. If that's the case, we go for step 3. Otherwise, it's a mistake. So the next step, we do one more check. We check to see whether the current request is less than or equal to the system available resources. If it is the case, we go to step 4. Otherwise, the current request is larger than the system available, therefore process I must wait. But even though the process I's current request is less than or equal to available, it does not mean process I can get the resource, because we need to verify that after this reallocation, the system is still safe. So the system, the resource request does the following. It pretends that this resource can be allocated. So we take the request out of the available, update the available by removing process I's request. And then add the process I request to the allocation, meaning assuming that process I receive it, and then subtract requests from the need array. So the new available, the new allocation, and the new need simply simulates the situation in which the request by process I has been satisfied. But of course, it's just an assumption. Then after we have this, and this, we call safety algorithm. So the safety algorithm uses the newly computed available allocation and the need to verify to see whether the system is safe. So if the safety algorithm says, okay, the situation you provide by through available allocation needs is safe, we don't need to change anything. We just give the resources to process I. Otherwise, process I waits. And the resource allocation tables are restored back to the original. That is, it requests back to available, subtract requests from allocation, and add requests back to the need. So here we have two places where process I, the requester, must wait. The first one is the request by process I is larger than the system currently available. Of course, it must wait. The second one is even though the current system available is good enough to satisfy process I's needs, but if we do that allocation, the system will be not safe. Therefore, we force process I to wait. So this is the banker's algorithm. Please review it before we continue. Okay, let's take a look at some examples. Now, assume the system has 5 processes, A, B, C, D, and E, and 3 resource types, X, Y, and Z. Resource type X has 10 units, Y has 5 units, Z has 7 units. At the time T0, we have this situation. I pull all 2-dimensional together, allocation, max, and need. And column X, Y, and Z are for the resource types. And the A, B, C, D, E, these rows are for process. Remember, available is a single-dimensional array. So A needs 7x, 5y, 3z, and so on. Now, this is the currently allocated resource. So need is equal to max minus allocation. And then the available resource is 3, 3, 2. Why 3, 3, 2? Look at here. B has 2 of x, 3x, and 2x. So the total allocated x will be 2 plus 3 plus 2, which is 7. And we have 10 maximum available. So x has only 3 units remains. So now for convenience, when we try to find a safety sequence, we always scan from top down. Every time we scan from top down, so that we all find the same safety sequence. So according to safe sequence, we compare need against available. So can A run? No, because 7 is larger than 3. The system does not have 7x available. Now let's look at the next one. B has 1, 2, 2, which is less than 3, 3, 2. Therefore, we could run B. After B is done, B would return 2, 0, 0. So 2, 0, 0. Here, the sum of 2, 0, 0 and 3, 3, 2 will be the new available, which is 5, 3, 2. So we have found our first process in a possible safe sequence. Then B is done, we remove B. Every time we simply scan from top down for simplicity. So currently the system available is 5, 3, 2. Can A run? No, because 7 is larger than 5. Can we run C? No, 6, because 6 is larger than 5. Can we run D? Because D's need is 0, 1, 1, which is less than 5, 3, 2. So we could run D. After D finishes, D would return 2, 1, 1, making the new available 7, 4, 3. Therefore, we have found the second process in this possible safe sequence, which is currently B and D. Now, the current available is 7, 4, 3. We scan the needed again. So A has 7, 4, 3. Well, it matches the current available, so we run A. After that, A would return 0, 1, 0, making the new available 7, 5, 3. So A would be appended to the safety to the safe sequence. So now we have 7, 5, 3. We scan down. Okay, we could run C, followed by, of course, the only one E. So what we have found is B, D, A, C, E. Due to the different way of scanning the need array, you may be able to find different safe sequences. Here are 2 more examples. Therefore, if the system is safe sequence is not unique. That's why we always insist to scan down so that we always work in the same order. Then we find the same sequences. Now, let's take a look at an example. Suppose now process B asks for 1x and 2z. More precisely, when process B wants to make a request, it builds an argument, which is 1, 0, 2. Is the system still in a safe state if this request is granted? Okay, B needs 1, 0, 2. So previously, we have 3, 3, 2 initially. So taking out 1, 0, 2, the current available is 2, 3, 0. Now, because B has already gets 1, 0, 2, so the original 1, 2, 2 minus 1, 0, 2, the new need will be 0, 2, 0. Now, the original B's allocation is 2, 0, 0. Now it gets more 1, 0, 2. So its new allocation is 3, 0, 2. So that's the first step. Pretending that this request can be granted, we construct a new set of table by updating allocation needs and available. So is the system safe? Yes. Yes. The system is safe because you could easily construct a safe sequence, BDEAC. Please verify it. Therefore, B's request can safely be made. Now, return to the results. Suppose E make a request 330. Now, because the system currently is 230, look at this table. So E's request cannot be satisfied because 3 is larger than 2. Therefore, E must be blocked. Now, what if in the same situation, A made a request to use 020? So if you make this request and 020 would make the variable to 020, it's going to be 210. 210. None of these 5 processes can run. Do you see that? So the system is unsafe. These 2 examples, the first one illustrates how to find a safety sequence. And the second example illustrates how the resource request is done. Now let's meet the old friend, the dining philosophers problem. In order to make sure the screen asset is enough, I can only use 3 philosophers and 3 chopsticks. So philosopher PI uses his left CI and his right CI mod 3 plus 1. You know this sequence would cause a deadlock. That's our first example of deadlock. P1 takes the left, P2 takes the left, P3 takes the left. Then P1 takes the right, and P2 wants to take the right, P3 wants to take this right. This request sequence will cause a deadlock. So can Bankruptcy algorithm overcome this problem, even though we have this sequence of requests? That is an interesting question. So again, we build a table. The right-hand side has the request. Initially, no philosopher has anything. And P1 needs C1, C2, P2 needs C2, C3, P3 needs C1, C3, C1. Because no chopsticks has been allocated to any philosopher. Therefore, need is equal to max. The current available would be 3 chopsticks. And here is the situation. So now P1 make a request to use C1. So P1's request would be 100 is here. So I use a diagram to illustrate. The dashed line arrow indicates a request. A solid arrow indicates the request is being granted. So assuming this request is granted, so C1 is no more available, and the C1 in the need matrix of P1 is 0 because P1 has it. So please verify that the system is safe by comparing this need and available. Obviously, the system is safe. So in this case, P1 has its left. Now, what if P2 request to use is left, is a dash arrow. So P2's request will be 0, 1, 0. Can this be granted? C2 is given to P2. Therefore, P2's need would be a 0 corresponding to C2. Now, in the system, C2 is not available. So again, you can easily verify that the system is safe. The safety sequence would be P2, it could be run, and P2 returns 1, then you could run P1 and followed by P3. Please verify this. Therefore, P1 and P2 has their chopsticks. Now, after P1's left request, P2's left request, now P3 wants to use his left C3. So P3's request is here. Assuming that P3's request is made, so the system gives C3 to P3, so the corresponding need entry is 0. Now the system has no chopsticks available. Now compare the need and available. There is no safe sequence. You cannot run P1 because P1's need is less than available, is not less than available. P2's needs is not less than available. P3's needs is not less than available. Therefore, we cannot find a safe sequence. As a result, P3 must wait, and the possible deadlock is avoided. So I mark a W here, indicating philosopher 3 is waiting with a dashed arrow. So here, P3 is waiting. Now, after P3 requests to use his left, which is blocked, then P1 wants to use his right one, C2. So P1's request will be right here. Because P1's request is not less than or equal to available, so the resource request algorithm would block P1. P1 and P3 are blocked, so P1 has a dashed line, dashed arrow indicating he is waiting for his right. And then P2 requests to use P3. So P2's request is this. So P2's request is here. Can this request be satisfied? So assuming that it can be satisfied, so C3 goes here, it becomes 0, the system has nothing remain. Now, the question is this safe? We could simply forget about P1 and P2 because they are waiting. But even though you are not forgetting about this P1 and P3, you could run P2. P2 would return 1, 1. After this 1, 1, you could run P1. And P1 would return 1. Here we have 1, 1, 1. Then you run P3. Therefore, running P2 is safe. So after P2 returns, you could either pick P1, right? Because we have 0, 1, 1. Okay, so because P1 and P3 are waiting, we pick P1. Because P1's needs is less than or equal to available, P1 can run. Note that P3 cannot run because its need is 1, 0, 1, which is not less than or equal to available. Therefore, you have to, P3 must wait until P1 finishes. As we said earlier, after P1 finishes, the system available becomes 1, 1, 1, which of course can satisfy P3's needs 1, 0, 1. Therefore, Banker's algorithm avoids possible deadlocks. the pattern, the circular waiting pattern we just discussed, is eliminated by Banker's algorithm. Now, 2 more slides before we end this lecture. Remember, we discussed a solution to the philosopher's problem. In this case, we require each philosopher must make a request of both chopsticks. So P1 make a request 110. P2's request will be 011. P3's request will be 101. Please use Banker's algorithm to show that this is deadlock free. And if you use 4 philosophers, that will even be more illustrative. We also mentioned a weirdo solution or lefty-righty solution. Please also do it with 4 philosophers or even 5 by hand. And finally, remember, after a process returns its resource, a waiting process waiting for its needed resource may be released if a waiting process request is less than or equal to the available and the system is safe. Remember that? In the philosopher's problem, when something is returned, we simply search the waiting list. So when searching for a waiting process to be resumed, one may implement some search order, such as priority and FIFO. What does that mean? Each process has a priority assigned by the system and stored in its PID, the process stored in its PCB, process control block. So the ordering of waiting processes could be based on priority. The first one has the highest priority. The second one is the second highest priority. The last one is the lowest priority. So you search this array, you search the waiting process by examining priority from highest to the lowest. Or you could use a first in, first out order. You build this waiting process list as a first in, first out. That is a commonly seen. But some systems prefer to use the so-called agent policy. So when a process enters a waiting list for a resource, the system assigns it a waiting priority. This priority is not the priority for the process. This priority is assigned for the waiting one. So how do we assign this waiting priority? If you wait longer, your priority gets higher. So suppose we have 2 processes, A and B. Process A waits for 3 seconds, and process B has waited for 5 seconds. Therefore, the waiting priority of B is higher than the waiting priority of A. Or you may use some fitting form: first fit, best fit, and worst fit, and so on. What does that mean by first fit, best fit, and worst fit? So suppose you have a request. Then when you search the waiting list in whatever order, you find the first one and give it the resource to it, regardless what kind of priority and order. Best fit goes as follows. When you search the array, the request of the waiting process, you find a request that's closest to the available. For an example, suppose the current available is 333, and we have 2 processes waiting whose requests are 111 and 222. So which one of this 111 and 222 being closest to 333? Of course, 222. So we release the process whose request is closest to the available. In this case, we try to give as much as possible to the process. The worst fit, on the other hand, is the opposite of the best fit. We try to keep as much resource as possible in hand. Again, the example, suppose available is 3, 3, 3. Process A's request would be 1, 1, 1. Process B's request would be 2, 2, 2. So in the worst fit, we give it to process A, because the difference between A's request 1, 1, 1 and the available 3, 3, 3 is the largest. So for best fit, I give the resource as much as possible to a requesting process. For the worst fit, I try to keep as much resource in hand as possible, in case some other processes may need my resources. So each of this feeding scheme has their own merits and drawbacks. I do not want to go further. For a final note, Banker's algorithm can easily be implemented with a monitor. You decide a request and the release monitor procedure, all the matrices would be in monitor. And you implement a resource request when a process calls request, the value goes into a resource request. Resource request does some checking and modify the available and so on, and call safety algorithm to ensure the allocation can be made safely and so on. Therefore, you have a powerful way to handle mistake, to handle a deadlock, so that the system is always deadlock free. Of course, resource utilization may be lower, as mentioned. The next lecture will be deadlock detection. Here, we do not have the maximum array. We just allow allocation to happen. But sooner or later, if the system has a deadlock, we must find some way to find, yes, we do have a deadlock, and who are involved in a deadlock. In addition to the deadlock detection algorithm, which is a modification of the Banker's algorithm, we also use a graph approach for detecting deadlock. So the third lecture is the last lecture of our deadlock discussion. The third lecture is a bit shorter. So let me stop here. See you next time, and good luck. And hope you understand deadlock better than before. Bye.